Okay, so we're going to dive into chapter 7. But the reason I put a note that I think it's a good idea for you to watch this recording before the test is we're starting off with a lot of revision on stuff that we already know. So I'm going to start off by talking about the survey that I sent out to you. Now, I know you wouldn't all have received that survey. I just sent it to people who on Canvas are registered as being in my streams. So I also sent it to a whole bunch of people that never watch my recordings, but that's what I did. This is what the survey looked like. First question, how do you rate the New Zealand government's response to the COVID-19 crisis? Scale of 1 to 10, so nice numeric variable there. Second question, so the previous survey I'd asked for just one word to describe how you were feeling about the lockdown. This time I gave some words so I could limit people's responses. So maybe there wasn't a word that actually really described how you were feeling, but hopefully you just picked something that was closest. And the last question, I'm going to talk a little bit about that one in a bit. Just wanted to share with you guys what everybody was saying. So here is how you're feeling about the government's response. So in general, pretty good, pretty nice responses from you guys about that, thinking that the New Zealand government's doing a pretty good job. Something around about an 8 is the most common. And there are a few people down the bottom end, but that negative skew is not got quite so many people down there. Here are the words that you picked. A bit of a mixed bunch. Lots of people sort of fine, which is quite encouraging. Kind of makes you feel like you're getting into the swing of things now. It feels like the new normal and it's all turning out okay. Quite a few people are still feeling quite stressed or quite bored. And what I did then is I condensed these into negative words and positive words. And this is what it looks like when I do that. So getting closer to 50-50 negative and positive, but more people, a higher proportion of people not feeling so great or feeling a bit negative about the lockdown. That's a bit of a shame. Okay, let's move my head out the way. So, talking a bit about the third question. So, it wasn't quite as simple as the other ones. What happened is when you clicked to go into the survey from the email that I sent you, you were randomly redirected to one of two versions of the survey. So one version was like the one I showed before. It just had the question. It was pretty bleak, quite a morbid question, but I wanted a numeric answer, so that's just what I went with. So sorry about that. Estimate how many people worldwide you think will die from COVID-19 by the end of the year. So some people just saw that question. Other people saw this one here. So in this version, they had some extra information to go on. So they had the current numbers as of the 16th of April. I was thinking, the reason I wanted to do this, I was thinking, well, maybe if people have something to go from, their values, the estimates they give will be different than if you're just pulling a number out of your head. And I thought maybe they'd be kind of similar because generally there's a lot of news at the moment about the virus and the death toll and how many cases and all that. And so I'm getting lots of updates and people might be aware of this number anyway, but having it in front of them maybe changes things. So I was interested to see what would happen. So what I've got following on from this is I have 6 questions based on this study, and we're going to cover the 6 chapters that we've already done. This first question is a chapter 2 question. You can see the chapter reference down the bottom corner there. And chapter 2 was all about whether studies, all about the difference between observation studies and experimental studies. So based on the study I've just described, which one of the following statements about that study is true? So pause the video, have a go at the question. Once you think you've worked out which one is true, you can join us back again for the answer. Okay, answer for this one. So I did say the reason that I wanted to ask you about something quite so morbid was to get a numerical response. So 1 is false, and we're not looking at a categorical response variable. The study is experimental because the treatment was randomly allocated to the participants. So that one is true. So you were randomly allocated to one version of the survey. The treatment variable there is, I guess, the type of question or whether you're given extra information or not. So the 2 levels, you're given extra information here and none there. So this is our true one. It was an experimental study. What does that mean? Well, it means as the result of an experimental study, depending on what you get when you analyze that data, is you're in a position that you might be able to make a causal claim about that treatment. The treatment was whether you had extra information or not. So at the end of all these questions and what we're looking at with the study, we might be able to say that giving extra information to somebody impacts what they put as the estimated number of deaths for this virus. So it might make the number higher or it might make it lower, or we might find that we're not able to say anything at all. Okay, statement 3. So we know the rest of them are false, but I will go through them anyway. So there's no random sample, so any result from the survey will not be useful. So it's kind of half true. There is no random sample, but that doesn't mean the results are not useful. It's an experiment, and we very rarely have a random sample of data for an experiment. So although we're not able to generalize to a wider population because we don't have a random sample, it doesn't mean it's not useful. The units for the study are the 2 survey versions. So no, the levels of the treatment variable are the 2 survey versions. The units are the who or what we get the data from. And so that was you, students, you were my units for the study. The study is observational because it is a survey. So we already mentioned how it's an experiment, so it's not an observational study. The surveys typically are observational because we don't have a treatment variable, but in this case we did. Okay, chapter 4 type question. So chapter 4 is commonly looking at sampling error and at non-sampling errors. The survey would have some non-sampling errors, but I won't talk too much about them. We're just focusing on one particular question, the question that was the experiment. And we're not too worried about sampling error because we don't have a random sample in the first place. Instead, something else that you'll typically get asked in a test based on chapter 4 is to use a string of random digits to randomly allocate. So there were 562 students that I sent the survey to. Imagine I numbered them from 1 to 562 and use the string of random digits down below to select people to get each version. So first I'm going to be selecting those who I give the no extra information version of the survey to. So take a minute, break up that string of random digits into sections as wide as you need or as long as you need, and see if you can figure out which is the correct one for the first 4 ID numbers. All right, so if you're ready, we're going to go through the answer. If you're not, just pause the video and come back once you are. So because my ID numbers go up to 562, they're 3 digits long, I need to break my string of random digits into sections 3 digits long. Then I need to go through, and any number that is higher than 562 is not going to be useful for me. This one would also be gone, and then we get to the end of it. I only need the first 4. So there are my 4 numbers. The other thing to watch out with doing questions like this are any repeats. So if I ended up with a number repeated, I would just discard the second time that number comes up. We discard any numbers that are too big, and we discard any numbers that are repeated. Okay, moving a bit backwards, thinking about chapter 1. So which one of the following statements describing the plot of the death estimates is false? Just as a note about the scale there, everyone's estimates were above 100,000, so, well, yes, nearly everyone's estimates were above 100,000. So 1 on the scale would be 100,000, so 50 on the scale is 5 million. Let's take a minute, read through those statements and see if you can work out which one is false. So if you need some more time, feel free to pause the video. Otherwise, we're going to go through these answers. So number 1, hopefully, most of you realize that that one was definitely true. We have definitely positively skewed data here. Positively skewed is when our tail is off to the positive end of the scale, so off to the right. The mean of the estimates is approximately 1.3 or 1,300,000. So it's pretty hard to see on a scale like this because it's all very, very bunched up down at the bottom. But yes, that is a pretty close estimate for the mean. The median is going to be lower than the mean because the mean is going to get pulled up by that positive skew. So if you looked at where the median was and then went pretty close to that, you get a pretty good estimate for the mean. But the median will actually be a bit lower than the mean. So that's our one that's false. Less than 25% of the estimates are greater than 600,000. So 600,000 is actually here, it's that upper quartile, and less than 25% are sitting above that. And yes, there's an outlier up here. So this is quite a difficult question because it's very difficult to read the plot with the scale being so bunched up. Hopefully you did as best as you could for that one. Oh, I'll just take all my scribbles off. So that's not really what we were looking at with our experiment. We wanted to know if there was a difference between those death estimates for the two groups. So I did 2 things here. I took out this outlier because it's so much higher than the next shortest or the next smallest estimate. I took that out so that we could see things a little bit better. And then I split into the 2 treatment groups. So be some good practice for you to pause the video here and have a go at writing down some statements describing those plots. Really typical question for them to ask you in the exam. Something similar to what we had before, with lots of statements having to pick which ones are true and false about the plot. Okay, so next moving on to sort of chapter 3 questions. So chapter 3 we did the randomization test. So we used the randomization test specifically on experimental data, but we're going to see a bit of a change to that through chapter 7. But what we were doing with the randomization test is we were trying to see if a difference that we observed in our experiment, so here we go, there's a difference of 1.24 or 124,000 in the median estimates for the 2 treatment groups. So the no information group had a higher estimate on average. That's the difference that we've observed. We'd like to think that it's a result of the treatment. So it's because that group had no extra information, that the estimates on average are higher. But we don't know that for sure, because remember, we always have to think, well, what about just chance? So if you just randomly split people into two groups, don't treat the two groups differently, but ask them to do something like give an estimate for the death rate. On average, those two groups will have different means or different medians, most likely, because just random chances at play, and people are different, and if you put different people into different groups, things are bound to be different. So we've got this difference that we've observed, 1.24, but we don't know what caused it. We don't know if it was the treatment or if it was just chance. So what we do is our randomization test is to try and investigate whether just chance is a plausible explanation for that difference. So we get this distribution down here, and that's going to help us. So I'll give you some time to read through the responses and see if you can figure out which one is not correct or a false statement. Once you're ready, restart the video again and come back, we'll go through the answer. All right, so I've not given you an easy question here, and probably just to make you feel a bit better, most of the questions that I'm doing at the start of this recording are a bit more difficult than what you'll see in the test. That said, do go through the past tests because they're the best indication you've got of how difficult the test is going to be. All right, let's start with A. So medians are better to use than means here because the data is more skewed for one group than the other. So why does that matter? Why does skew matter? So skew will pull the mean in the direction of that skew. So our no info group is more positively skewed than the info group, which means that if we were comparing the medians, they're only 1.24 apart, but the mean for the no info group would be quite a bit higher because of that positive skew. So you'd get a bigger difference, which is kind of exaggerating a possible treatment effect. So it's supporting your argument, but that's not what we're trying to do. We're trying to do unbiased, an unbiased test to see what's going on. So to take that kind of effect out of it, we'd really want to look at the medians. So that one there is true. The randomization distribution shows the set of differences, in this case between medians, we could expect to get if the information had no effect on the death estimate. So if the treatment had no effect on the response variable, that's basically saying if chance was acting alone. And remember, our randomization distribution, that's a picture of chance world. So what we would expect to get if only chance was acting. Our treatment does nothing, it's all just chance, that's what we would expect to get. So B is true as well. C, our tail proportion is less than 5%. It is just, it's 4.8%. The re-randomized data, so we're looking at the middle panel, shows groups that are different due to chance alone. So looking at those two groups there, it's hard to see a difference at all. They look actually pretty close, but they are slightly different. But what's caused that difference? Just chance. So this panel here is also chance world. This panel at the top is the real world. And in the real world, we don't know what caused that difference. Might have been just chance, might have been the treatment. These two panels, only chance is acting. This is our model. This is what we're modeling. We're modeling chance, the chance effect. We're looking at what would happen if it was just chance. We're looking at that over and over and over again because we can do that. We can simulate chance. We can't simulate the real world. It's it happened in the experiment. We don't know what was going on, why it happened, but that's what we got. Okay, so E must be our one that is false then. So E says we have no evidence against the chance acting alone explanation for the observed difference. So because our tail proportion is fairly small, it's less than 5%, and that was kind of the cutoff that we used. Because our tail proportion is small, we would say it's unlikely that we would get a difference of 1.24 just by chance or in chance world. Unlikely for chance world, it's unusual for chance to get a difference that big. So we do have evidence against the chance acting alone explanation. It would be unusual for chance acting alone to cause that difference. Okay, quite a lot going on in that one. Unfortunately, it doesn't get much smaller. So what we've got here is chapter 5, so looking at bootstrap confidence interval. Now, previously, we've only produced confidence intervals when we're looking at making a sample to population inference. So what I mean by that is we have some wide population we want to know something about, some parameter, some value for that population we want to know about. We can't access all the data for the whole population, so we take a random sample, and then from that random sample, we can estimate back to the population. Now, that's not what's going on in this case. In this case, we have experimental data that wasn't from a random sample. So why would we do a confidence interval? Well, it's a little bit complicated, and I'm going to talk more about it in some recordings later on in chapter 7. But for now, I'm going to say that my parameter of interest is the underlying median death estimate, or rather the difference between the underlying median death estimate for the two groups. So this word underlying, what it means is 1.24 is our observed difference. That's from our data. And what I'm saying is that this is an estimate for some bigger parameter. There's some bigger picture here that we don't know the value of the difference between the medians. And that bigger picture, it has this parameter, which is the underlying median. So underlying is just an indication, it's like bigger picture, bigger than just our data. I know that sounds a bit confusing, but when we're doing confidence intervals like we were before, we had a parameter and it was the statistic for our whole population. Here our parameter is our bigger picture statistic, but we're not really sure exactly what that big picture is. So we just refer to it as underlying. Technically, and there's a note in your blue pages about this in chapter 7, technically what underlying refers to, and you don't really need to know this for your assessment, but it is good to know. Technically what it means when we're referring to experimental data is the underlying mean or the underlying median for the information group would be if everyone who participated in the experiment was in the information group, this is the mean we'd expect them to get. That's the underlying mean. So it's if everybody that participated was in that one group. Because we can't extend it beyond the participants we have, because there's too much sort of non-sampling type bias from the people that are in our experiment to people that aren't. So we can't extend out or generalize anything to a wider population. It's still just the people that were in our experiment, but we're kind of doubling up. We're kind of saying, well, what if they were all in one group? What would our mean be then? And that's where this underlying comes from. Short story, underlying, think big picture parameter. Okay, so with that in mind, we have this parameter, the difference between the underlying means for the two groups, underlying medians for the two groups. 1.24 as our estimate for that parameter, and I've used VIT to generate a bootstrap confidence interval for that parameter. So one of the 5 statements on the right is not a correct interpretation of that output. So have a read through those, pick the one that you think is false, pause the video. When you come back, we'll go through the answer. Okay, so make sure you pause the video if you're not quite ready, because we're going to go through those statements. So let's read A. The bootstrap distribution is skinny, which tells us there's not very much sampling error in our estimate. So that one is true. So remember what our bootstrap distribution is it's an estimate for our sampling distribution. Or another way of putting it is it's an estimate for what we would the variation we would expect to get if we took new samples over and over and over again from the population. So if it's really wide and really spread out, that means our sample statistics are varying quite a lot. They're different, quite different every time we take new samples. And that tells us we've got a lot of sampling error. A nice skinny distribution like this tells us the opposite. It tells us that we don't have very much sampling error and that the variability in our estimates, sample to sample, is nice and small. So a nice skinny distribution like that, you can see it also gives us a narrow confidence interval. So it's all really good stuff. So not very much sampling error, nice skinny confidence interval. We can be very precise with our estimate. Okay, B, the lower limit of the confidence interval is negative. So it is plausible. So remember, our interval gives a range of plausible values for the parameter. So anything in that interval is plausible. So it's plausible that the underlying median for the no info group is lower than for the info group. So it doesn't matter which way around those two groups are, either thing is plausible because we've got a positive end and a negative end to our confidence interval. So it's plausible that the info group is lower, it's plausible that the no info group is lower. Both of those are plausible within that confidence interval. C, the confidence interval is not symmetric. So when we do norm-based confidence intervals, because we do a calculation to obtain them, our estimate is always sitting smack bang in the middle, and then we add on the margin of error, subtract off the margin of error, and that's how we get our interval. We build it to be perfectly symmetric. In bootstrapping, because it's simulation-based, our bootstrap distribution doesn't always come out to be perfectly symmetric. And in this case, our data is quite skewed. And so our bootstrap distribution has come out to be a little bit skewed as well. It's quite hard to see because it's quite condensed. But what that means is our intervals are not always perfectly symmetric. And in this case, it's not a perfectly symmetric interval. It doesn't mean it's wrong or it's bad or anything like that. In fact, it's slightly better because it's based on the reality of the data. So yeah, it's not symmetric and we don't need to worry about it. D, it is believable the underlying median for the no info group is 200,000 more than for the info group. So 200,000 more would mean that the median for the no info group minus the median for the info group is 2. 2 sits in our interval, so yes, it is a believable or a plausible value. E must be our false one again. So in the resample data, so we're looking at that middle panel through here, it is possible that an estimate that was originally in the no info group might be in the info group. So that is false, as we expected, because one of them had to be. But the reason it's false, and the reason I put this question in here, is I wanted you to think really carefully about the difference between the randomization test and bootstrapping. They look very similar in terms of what's happening on the screen, but they're doing very different things. When we resample in bootstrapping, the group and the number stay stuck together. So an estimate, like this estimate here of 80 in the no info group, it is always a no info group estimate. Now, it just so happens in this particular resample, it wasn't selected because we resample with replacement. This one here of 65, that was sampled, put back in, sampled again, put back in, and sampled again. You can see it's come out 3 times. So sometimes values are chosen for the resample, sometimes they're not, sometimes they're chosen more than once, but they never switch groups. In a randomization test, you can see this one here was no info, and now it's info. They do switch groups. Because in this chance simulation here, what's happening is we're stripping all the labels off because we're assuming, or we're trying to see what we would get if there's no treatment effect. We're taking the treatment off and then just randomly allocating it because it doesn't make a difference. So they're quite different things. Last chapter to recap is chapter 6. So looking at a 95% confidence interval. And this is a 95% confidence interval just on a single mean, the mean for the no info group. And there it is there, and we can see the sample size and the standard deviation. I want you to have a go reading through these 5 statements and choosing the statement that is false. I'll give you a minute. Okay, so let's go through these. So I've totally flipped it up this time, and the false one is A. If it was twice the data, the interval would be half as wide. The reason for that is that when we sorry, looking at something weird. When we generate our confidence interval, the width of the interval does change when the sample size changes, but it's not a one-to-one relationship. We need n squared data to have, well, we need 2 squared times the data to have the width of the confidence interval. So we need 4 times the data to get an interval that's half as wide. So that relationship between sample size and confidence interval width is that squared square root relationship. So B is our, A is our false one already right off the bat. So B, if there was a mistake in recording the standard deviation and it was actually 2.5, so a lot smaller, the new calculated confidence interval with its corrected standard deviation would be narrower. So the less variability we have in our data, the more consistent our estimates will be, or the smaller our sampling error will be, so our interval will narrow. C looks at changing the confidence level. When we want to widen our confidence, we have to expand our search. So a 99% confidence interval will be wider. Less data, the interval would be less precise. So another way of saying that is less data and the interval would be wider. And the degrees of freedom for this calculation was 45. So degrees of freedom of n minus 1. So quite a lot going on there, but this is a bit of a summary of what we've done in the first 6 chapters, what you're going to be assessed on in the test, and hopefully what we already know. So how to describe data from plots. Chapter 1, while you're studying for the test, you also need to think about calculating proportions from 2-way tables. That was a big part of what we did in chapter 1 as well. Chapter 2, mostly we looked at trying to tell if a study is observational or experimental and then what this means. So experimental, meaning that we can take the results and potentially make a causal claim. Observational, meaning that we can't do that, but we can still look for a link or some kind of relationship. Chapter 3 was the randomization test. Chapter 4, looking at non-sampling and sampling errors. Remember that a confidence interval only corrects for or only takes into account sampling error. It doesn't do anything to fix non-sampling error. If you want to fix non-sampling error, you have to go back and do your study again. In the design process that you can try and eliminate as much non-sampling error as possible. Then chapters 5 and 6, we're generating and interpreting confidence intervals, but using different methods. So what we're going to look at in chapter 7 is similar to what we did in chapter 3. We're observing some data. We might look at experimental data, but we're also going to look at random sample observational data. And we look at this data and, like, for example here, we notice that there is a difference. But we're not really satisfied with just that. Is the difference we're observing, is it like worth getting excited about? Is something really going on? Are they really different? Or is it just a feature of this particular data? Or is it just chance acting alone? And chance acting alone for an experiment we're quite familiar with. But what does chance acting alone mean when you have observational data? Well, if we're taking a random sample, is it possible that when we randomly select our sample for one group, that we happen to get people that pick really high numbers, and when we randomly select our people for group 2, we happen to get people that pick really low numbers. So even in random sampling, there's that element of chance acting, and it could be that our differences are just due to chance. So we want to have a way of testing whether what we're observing is worth getting excited about. So this is what we're going to go through in chapter 7, and there's a bit of language in chapter 7, but not actually a lot of new stuff. A lot of what we're doing are things we already know about, but we're starting to use some more formal and technical language. So I'm going to go through an example from back in chapter 3, and we're going to look at it with a chapter 7 lens and see how it looks different. So hopefully you remember this experiment that we did back when we were still in actual lectures. So you were randomly allocated to 2 groups. So it was an experiment because it was random allocation to the group. Group A saw one photo, Group B saw a different photo, and then from the photo you had to estimate how old I looked in that picture. And you can see the data there, Group A, Group B. Group B on average gave higher age estimates than Group A. Now here's what we didn't talk about at the time. So we didn't talk about how there was a parameter. So we didn't encounter this word parameter until chapter 5 when we started doing confidence intervals. But there was something we were interested in here. And like I mentioned before, it's not the population mean or the difference between the population means. There's no Group A population, Group B population. We don't have a random sample, so it's not what we're trying to generalize to. But there is some bigger picture here, bigger than just the data that we're looking at. And so we refer to that as our underlying distribution or our underlying means. So our parameter of interest here is the difference between the underlying mean age estimates for Group A and Group B. And we can use symbols like we did. Oh my goodness, that wasn't meant to happen. We can use symbols like we did back in chapter 5. So I'm going to go mu B plus mu A. So that's our parameter of interest. So this first step, really similar to what we did in chapter 6, but we're now trying to throw it into experimental data to see how it works. Okay, the next 2 steps are about the hypotheses. So chapter 7 is about hypothesis testing, and actually the rest of the course is about hypothesis testing. So we want to get our head around what this idea of a hypothesis is as early as we can. So what we have with the hypotheses is there's actually 2 of them. There's the null hypothesis and the alternative hypothesis. And we can think about these as 2 competing and complementary statements. And by that, I mean either the null hypothesis is true or the alternative hypothesis is true. There's no third thing that could possibly be true. So they have to perfectly complement each other. Our null hypothesis is always sort of a a safe fallback position. And our null hypothesis would be that there's nothing interesting going on here. So remember, what we're doing is we're always trying to see, like, is there really something going on? So our null hypothesis is, no, there's nothing going on. It's boring, there's nothing happening, just chance is acting, there's no real difference. So in this case, we're looking for a photo effect. So our null hypothesis is chance acting alone, there's no photo effect. Chance acting alone. The alternative hypothesis is the opposite of that, and it links to the research question. So when you first do the research, or the researcher does the research, or in this case, I do the research, they're trying to find something out. So I was trying to find out if there was a photo effect. You know, I thought that photo B would make me look older and would make you estimate that I was older. So that's my alternative hypothesis. That's what I kind of want to find out. But I don't have that as my null, I have that as my alternative. And I'll talk a little bit about why they're that way around later on. So that's what we've got, our two competing statements. Chance is acting alone, chance is not acting alone. There's no photo effect, there is a photo effect. Okay, so we've set up some statements now, our parameter and our hypotheses, to just formalize what we have already done. So like I said, chapter 7, not a whole bunch of new stuff, it's just formalizing some of what we've already done. Let's go back and look at some other examples from chapter 3. So there was also this one here, looking at the drink times for the straight glass and the curved glass. So the parameter is again going to be the difference between the means. The mean for the straight glass minus the mean drink time for the curved glass. Okay, so how would we talk about that? Well, we'd say it's the difference between the underlying mean for the straight glass and the underlying mean drink time for the curved glass. So underlying, we're going big picture here. Parameters are always big picture. So ideally they'd be about the population, but when you haven't got a random sample from a population, you're just talking about some underlying distribution that you want to generalize to. The underlying means. Our null hypothesis, I'm going to use some symbols here. And I might just change my pen color so that you can see that better. There we go. So here's the symbol for the null hypothesis. It's sometimes referred to as H0 or H0. And our null hypothesis here would be, same again, that chance is acting alone. And if chance is acting alone, we would expect no difference between those two means. We'd expect them to be the same. Another way to write this, which is more common, is that the difference between them is 0. Our alternative hypothesis, which is sometimes referenced as H1, is the complementary to that. So it would be that the straight-sided glass has a longer drinking time than the curved-sided glass. And we can show that again like this, is greater than 0. Now the reason those bottom notations are more common is because they give you a number, and that number is called the hypothesized value. So it's what you are hypothesizing the value for the parameter to be. So under the null hypothesis, if chance is acting alone, we would expect the difference between the underlying mean for the straight-sided glass and the underlying mean for the curved-sided glass to be 0. That's our hypothesized value for the parameter. Oh, carried away there. Our alternative hypothesis has the greater than symbol in it, and that tells us that we have a one-sided hypothesis. I'm definitely going to talk more about that later, but for now just kind of put it in the back of your mind. There's a greater than or a less than sign in our alternative hypothesis, It's a one-sided hypothesis. Okay, let's look at the caffeine one. So this one was a bit different. We didn't have an exact measure. If you remember, what we were looking at was this one here, the observed average absolute deviation from the overall mean. Remember, it went on and on. So our parameter is that, but big picture. So instead of being the observed, blah, 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 we would say the underlying, blah, blah, blah. That's our parameter. Our null hypothesis, so if chance is acting alone, we'd expect all these groups to be really, really similar. So we'd expect all their medians, all their means to be on the overall mean. So our null hypothesis is that our parameter, and I haven't got a symbol for it this time, so let's just put the little arrow. That our parameter would be equal to 0. And our alternative hypothesis, there is something going on, then that arrow gets bigger and bigger and bigger, so it's greater than 0 is our alternative hypothesis. Another one-sided test there. We can do these tests when we're looking at proportions as well. So our parameter in this case is going to be a proportion, and it's going to be the difference between the proportion for the dolphins minus the proportion for the no dolphins. And we're using p's, not p hats, because we're talking parameter. So this is our underlying proportion for the dolphin group and the underlying proportion for the no dolphin group. Underlying proportion. Our null hypothesis, well, if there's no treatment effect, then both these groups will give, will have the same proportion. So that would be that the difference between the two proportions is 0. Sorry, I put in twice. That should be no dolphin. Our alternative hypothesis is that the dolphin treatment has had an effect. So the proportion for dolphins is going to be bigger than the proportion for no dolphins. So our alternative hypothesis, one-sided again, that the difference is greater than 0. So quite a lot of new stuff that we've learnt there about these hypotheses, and there's still more to go with those, but we'll leave it at that for now in terms of what the parameter and our hypotheses are. The next thing we want to do is get into actually testing this out and seeing if there is anything worth getting excited about, and whether which one of our two hypotheses, null or alternative, seems to be the most convincing. So we know back from chapter 3 what we did was a randomization test. And that's still what we would do, but we've got a little bit of extra language. So in the top panel there, the data, what we called back in chapter 3 our observed difference between the means. That's still what it is, but we can refer to it now as the estimate, because it's an estimate for the parameter. If we don't have a parameter, we don't have anything to estimate, but now we've defined we have a parameter of interest. So our observed difference is an estimate for that parameter. Change of language. When we get down to the third panel, the re-randomization distribution, the red arrow that we place here, and you can see the red arrow is the same length as the estimate. It is that same arrow. But what we call it when we're putting it on the re-randomization distribution is we call it our test statistic. And again, more on that later. So this is just language change for now. So it hasn't changed what it was, but now we call it the test statistic. Our tail proportion has changed names as well. It's now called a p-value. And the reason it's changed names is because we're now associating it with our hypotheses. So the hypotheses are what we're testing out. So we now have a p-value, not just a tail proportion. There's some change in names, but not actually anything really new. Just a bit of a reminder, I said back when we did the last example, that randomization distribution, each dot represents something that occurred just by chance. Okay, so we pop that in there. The next thing to do would be to interpret the result of the randomization test. And we're now saying that we're interpreting the p-value, because that's now what our tail proportion is called. But this interpretation is the same as what we did in chapter 3. We've got a small tail proportion there, you can see 1.3%. Our p-value was 1.3%. It's nice and small, so we would say it's unlikely chance acting alone would produce a difference as big. I don't know where I got 10 from. That should be 13.3. And because this is an experiment, we would say that we have evidence of a treatment effect, a photo effect. Looking back to our hypotheses, what we've basically said is we have enough evidence that we can get rid of that null hypothesis and say that the alternative is true. So we've said it's unlikely that the null hypothesis is true. It's unlikely it's just chance. So we're saying that there's evidence of a photo effect. So that's our alternative hypothesis. Quite a lot to get your head around, I know. Let's look quickly back at the examples from before. So our estimate is 4.21. And we can say it how we did back in chapter 6. X bar symbols for means. Our test statistic, looking at that arrow there, is also 4.21. And our p-value is our new name for tail proportion, 0.3%. This one here, our estimate, is that arrow, however big that is. And that's also our t statistic, because you can see it put on the re-randomization distribution as well. Our p-value is 1.6%. Dolphin one, our estimate, p hat dolphin minus p hat no dolphin, 0.467. Our test statistic that we place on the randomization distribution, 0.467. And our p-value in this case was 1%. That looks like a terrible percent sign, but I think you know what I mean. 1%. Okay, we'll skip that last one again. All right, so that's pretty much as far as we got to back in chapter 3. We've changed the names of some things, but nothing truly radical happened. In chapter 7, we keep going though, we don't stop there. So we said, okay, there was a treatment effect. We've got evidence against the null hypothesis. Evidence against chance acting alone. So said, okay, we've got evidence against that, evidence for that, but just because there is a photo effect, doesn't really tell us anything about what that photo effect is. So we want a confidence interval as well. We don't stop at our p-value at the result of our randomization test. We keep going and we get a confidence interval as well. So here's our confidence interval. I've done a bootstrap interval, and just a reminder about what the dots in the bootstrap distribution mean as compared to the randomization distribution. So we can round our confidence interval there to 4 up to 24. And when we interpret that, it's a fairly safe bet because it's just a bootstrap interval. It's not a 95% or 99% norm-based confidence interval. It's a fairly safe bet. The underlying mean, so referring to our parameter here, which is the underlying mean age estimate for group B, somewhere between 4 and 24 years higher than the underlying mean age estimate for group A. So now that we've got the result of our randomization test, and our confidence interval, we can sort of wrap them together in a conclusion. So we can claim there was a photo effect. That was from our test. Then we can say how big that photo effect. So the photo effect is likely to produce a difference in the averages of between somewhere in 4 and 24 years, which is kind of crazy. That just by changing the photo a little bit, on average, people think I'm maybe only 4 years older, but up to 24 years older. Remembering, of course, that only is talking about the parameter, only about the mean. It's not talking about individuals. So individually, there can be huge differences. Okay. So what we've just done at length are the 10 steps that we're going to be using in Chapter 7 to perform a hypothesis test. Some of it is a bit new, and most of it's only new in language. It's not new in skill or what we've actually been doing. With confidence intervals, I used a bootstrap confidence interval, but I could also use a norm-based Chapter 6 interval. That would be fine too, they both work. And with our p-value, we got it from a randomization distribution, but we're going to see a theoretical method for getting a p-value as well. So there's going to be 2 methods for getting a p-value, just like there are 2 methods for getting a confidence interval, and you can mix and match them however you like. So in summary, when you're doing hypothesis testing, first you're looking at some data and you're like, these means, these medians, these proportions, they look a bit different in my data, but is it just my data or are they really different? So you do a hypothesis test and then you find out that they are different. You get a small tail proportion, you get a small p-value. You're like, oh, cool, they're different. But like, how different are they? Then you need a confidence interval for that bit. Okay, so that's quite a lot to take in. Have a bit of a breather, maybe go do some more revision for the test. And when you're feeling appropriately psyched up, you can get into some Chapter 7 examples in the following recording.